So here's the story of these two cars. First of all, A is minding his own business and not moving, and B comes and crashes into him. Bam! Right? Then after the crash, both cars are now moving in the direction that B used to be moving in. So I call the original velocity regular V, B's after velocity V sub B, and A's after velocity V sub A. But then there's friction, and eventually the two cars stop. And they give you the two distances it takes for them to stop after the crash. All right? So the first questions ask from these distances to calculate these velocities. So we have distances, we have velocities, and we know that friction happened, so that must be the work kinetic energy theorem. So for parts A and B, we're going to use the work kinetic energy theorem, which says that the work is equal to the change in kinetic energy. Well, the kinetic energy at the end is 0, and so the kinetic energy at the beginning is the only one that we're concerned with. So it's going to be 0 minus 1/2 mv squared, with the m sub a or the m sub b and the v sub a or the v sub b, depending on which car you're dealing with. All right? And then the work, well, we're going to concern ourselves with the frictional force, which in between here and here, the friction operates that way, but the displacement was this way. And so that means that the angle between them was 180. We put that in the calculation. And we also know that the frictional force is always mu times the normal force. And in this simple, flat situation with no other forces acting, that means that the friction is equal to mu mg. So we'll put that over here, that the work is equal to the friction times displacement times the cosine of 180. And the friction is mu mg. The displacement is d. Cosine of 180 is -1. And so that's going to be equal to -1/2 mv squared. The masses cancel out. And now we can calculate the velocities. Each velocity is going to be the square root of 2 mu g d. And then for part C, they ask you to use conservation of momentum to figure out this initial velocity here. Well, that's pretty easy. We have before and after. We have cars A and B. Car A had no momentum before the collision back here, it's not moving. But car B had mass of car B and the initial velocity v. That's what we're trying to find out. Afterwards, we have this situation right here. So that's going to be MAVA, MBVB, which leads us to this equation. MB times the original velocity is equal to MAVA plus MBVB.